The last problem in the packet is called the swimming pool problem. And in this problem, we're building a rectangular swimming pool, and it's to be built with an area of 1,800 square feet. The owner wants to put in a 5-foot wide cool decking along the longest sides and a 10-foot wide cool decking at the two ends. Cool decks should be installed around the entire pool so you can sort of walk around the whole pool. We want to find the length and width of the smallest piece of property in which the pool can be built to satisfy these conditions. So that area we're given is just for that inside pool. So we could imagine, okay, here's our pool. It has an area of 1,800 square feet. And we're going to have this long side be known as X and the short side be known as Y. We don't know the dimensions of that yet. But then they want to put around a deck around the outside. So let's do orange for the deck. And on the long side, it's going to go out 5 feet. So 5 feet, 5 feet. And on the short sides, it's going to go out 10 feet. And then we get a sort of bigger piece of property. That's the pool plus the deck. And that's the area we're trying to minimize. So we're going to end up with sort of multiple areas here. Now, if I wanted to describe the area of the entire property, think about that, the sort of length right here would be the Y length, but plus the 2 5s. So I would describe that as 10 plus Y. And this longer side would be the X length of the pool plus the 2 10s. So that would be 20 plus X. All right, so we have a bunch of dimensions. Now let's write some functions. Well, the area of the pool is 1,800 square feet, and I would find its area by taking X and multiplying by Y. Helpful. I'm probably going to want to solve for one of the variables eventually, so I'm going to just rewrite Y equals 1,800 divided by X. Okay, I got that. Now the bigger property, I'm going to call that my area function, A of X. And I would find that area by doing the 20 plus X, which is the dimension of the long side, times 10 plus Y. And I could substitute in at this point, but I'm actually going to wait and distribute first and then plug in afterwards. Because if I distribute first, I get 200 plus 10x plus 20y plus xy. So here's why I waited to distribute. If you notice, I have an xy here. Well, I have an xy up here. That's equal to 1,800. So I'm going to just plug 1,800 right in for that one. And then I have y here, and I know that y is equal to 1,800 over x. 1,800 times 20 would get me 36,000 all over x. And then I have plus 10x, and I still have that plus 200. And I could combine my like terms, and I'm going to rewrite that x to a power. So with my like terms combined, I get 2,000 plus 10x plus 36,000 x to the negative 1. And now a is in a form that's not too difficult, hopefully, to take the derivative of. A prime of x would, the constant goes to 0. 10x's derivative is just 10 minus 36,000 x to the negative 2. And now this is a form that should look somewhat familiar. We've dealt with this equation a number of times. This one might look a little different, but we're going to treat it sort of the same way. So we're looking for our critical values. So we're going to go in, and I'll change colors here. We're going to make 0 for our a prime of x. I'm going to rewrite that negative x to the negative 2 power as x squared in the denominator. I just prefer it that way. I'm going to add that over to the left side. So 36,000 over x squared equals 10. Multiply both sides by x squared. I get 36,000 equals 10x squared. Divide both sides by 10, gets us 3,600 now equals x squared. And I would take the square root to undo that squared. I can't have a negative solution because the dimension of a pool can't really be negative, so I'm only looking at the positive root. And so the positive root would come out to be 60. Okay, now stop and consider what the problem's asking. That 60 is the inner dimension of the pool. It's this length right here. And I could plug back into this original area. 1,800 divided by 60 would get me the other side of the pool is actually 30 feet. So I have a 60-foot by 30-foot pool, but that's not what I'm being asked for. I'm being asked to find the length and width in feet of the smallest piece of property on which this whole thing would be built. So I actually need the overall dimensions. So 60, I'd actually need to add it to 20 and get 80 feet, and then that 30 would get added to 10, 40 feet. So the property would need to be 60 feet by 40 feet to satisfy the given conditions. And hopefully that helps. This problem was complex in sort of interpreting the diagram, but once we got into the calculus, it shouldn't have been too bad. And again, I didn't do my first derivative or second derivative test, but at this point, I'm hoping that that's something you're comfortable with and can do on your own. All right, and that is the last problem in our optimization packet. Yay!